Chemistry ASMR at your service. So I'm just gonna be chilling here for a while, drawing with my calligraphy pen and doing some chemistry. I am a chemistry professor, and this is what I do on a Saturday night. I find it really relaxing, and those of you from my YouTube channel, or if you haven't seen my YouTube channel, you can check that out too. They have found it to be, from what they tell me, really relaxing, but also they appreciate that it's legit. This is legit chemistry. I've been teaching it for 22 years, and I think I've gotten pretty good at it. And I also just love doing calligraphy, so I've decided to combine the two. And here I am. So if you have any questions, feel free to put them in the chat, but otherwise I'm just gonna do my thing. And I was trying to think about what to talk about tonight, and I was thinking about the periodic table. And I know periodic trends is something that trips people up sometimes, so that might be a good place to start this evening. So that's where I'm headed. And always when I start this out, my pen always needs a little warming up. So as I said, I use these calligraphy pens, which are just really cool, especially these ones that are I don't know what the deal is with my focuses tonight, but anyway, this is called an oblique pointed pen, calligraphy pen, and just put in these. This is called a nib, this part, and I've got my India ink here. It's really fun when you have different colors of the ink. And sometimes these pointed pens, they don't grab onto the ink, so I just have a side here just to practice and just make sure, okay, are you doing your thing? So these pens, some people use them for, fancy calligraphy, like invitations or something like that. And they're actually also used for drawing, like cartoons and some illustrations and things like that. I know, it's early or it's late. I don't know which one it is, but hi, Pistol Top. Good to see you here. I'm going to be doing chemistry. And I got my periodic table, got my calligraphy pen, and we're just going to go for it. So I always love starting out just giving it a header, and writing out. And I am not trained in calligraphy, I just kind of make it up. So I know there's some calligraphers who there's a certain style you're supposed to do, but I don't do that. I just do whatever I want. I'm going to start out and just talking about atomic radius. And I gotta say, if you have insomnia, this is just the best. I am gonna put you right to sleep. Okay, so when I say atomic radius, what am I talking about? Well, this is essentially you also might wonder who cares. Ooh, yeah. Elementary. Okay, yeah. It's always good to have a nice background of some fundamental stuff before you start getting into the heavy duty stuff. That's awesome. So when we talk about atomic radius, we're essentially talking about just the size of the atom. And if we first just look at the periodic table, and we notice above each element, and I'm really hoping this is in focus. Where's the best focus? I don't know. But above each element is a number. Here, 1, 2, 3, 4, etc. The atomic number. So that's the number of protons that are in the nucleus, and it's also the number of electrons if it's a neutral atom. And so it might make sense that we just generally get bigger as we add a proton and as we add an electron. That could be the logical conclusion if we're looking at the atomic radius and what the trend would be. But that is not the case. It's actually very interesting how it plays out. And I'll start out just talking about the general trends, and then we can also talk about the exceptions. Okay. So, generally speaking, on our periodic table, we can talk about the columns, which are also called groups. Or I should say they're formally called groups on the periodic table. And as you go down a group, each time we go down, let's look at hydrogen, lithium, sodium, potassium. As you go down, each time we have filled up an entire shell of electrons by going across, and once you get to this beginning of this new row, this is a new shell of electrons. It's kind of like an onion, layers of an onion, and we've added a new layer here. It fills as you go across, and then here it's a new layer. So as you go down, it's always going to be larger. So that is a very nice, predictable periodic trend as you go down a group. It's always going to be larger. Or in other words, the radius increases. Sorry about that. Okay, but some stuff going on. So okay, so what is happening? This is actually counterintuitive. So on the periodic table, the columns here, these are called groups. As you go across the rows, that's called a period. So across a period, let's just focus right here. You might think that because we're getting more and more protons as we go across, 5, 6, 7, 8, 9, 10, that we would have a larger radius. But in fact, it is the opposite of that. So check this out. Across a period, the radius, I'm going to have to readjust my mic so I stop hitting it with my pen. Okay, across a period, the radius decreases. All right, why? Why is that? How can that be? So what is happening here is that you have with boron 5 protons, and carbon you have 6. That means that carbon has a greater pull on the electrons, pulling them in, because there's 6 protons. The 6 protons, let's do a comparison. Protons are positively charged. Alright, so if we look at boron and do a comparison with carbon. Yeah, this is challenging. And so right now I'm going to talk about it with a point of view. We're not even going to necessarily look at the details of orbitals. We'll just talk about it more generally. But we can also talk about orbitals. Definitely. I love talking about orbitals, and they are challenging, so I think it will be helpful if we can talk about them a little bit. So with boron, as I said, we have 5 of these protons in the nucleus. And I'm going to ignore neutrons. Neutrons are neutral entities that are in the nucleus as well, but we'll just think about the protons here. And boron has 5, whereas carbon has 6. So we've got 1 additional proton in the carbon. And that means that if we think about those electrons that are around, and I won't say exactly what they look like or where they are in the orbitals, but we'll just say they're somewhere out there. But what we do know is that 2 of those electrons are closer in, both boron and carbon. And then the other 3 that boron has are a little bit further away, so we'll put them out here in the second shell, further away. Carbon, neutral carbon, must have a total of 4 electrons in this external shell, 2 electrons in the internal shell to balance out the 6 protons there. So the net result here is that because there are more protons in carbon than there are in boron, these protons are pulling in these electrons in this shell right here, in this outermost shell. Whereas boron, there's only 5. Oh, hey, thank you. Yeah, you should go to sleep. I should go to sleep, actually. Yeah, sleep well. And so glad you stopped in. Thank you, Pistol Top. And have a good sleep. And yeah, so these 5 protons, these are not as strongly pulling these 3 electrons from that outer shell. So 6 protons stronger, pulling them in. And that results in a smaller radius, even though there are more protons. So that is essentially the reason why, generally speaking, we have a decrease in atomic radius as you go across a period. There are exceptions to that, but right now we're just talking about general trends. Okay. Once again, I love the idea that I'm putting people to sleep, which I think is so funny because, you imagine a chemistry teacher is teaching in class, and if students were to fall asleep in class, they would just be so insulted and take it personally. And for me, doing this, it's the complete opposite. So if you fall asleep, I am like, yes, I have done my job. So please fall asleep, and hey, maybe you can learn something by osmosis. All right. So I wanted to talk next about ionization energy. And this periodic trend is actually very closely related to atomic radius. So, this ionization energy, oh come on, pen. Oh, it's so sad. And you might wonder, why don't I just use a regular pen? Well, it's because these are so awesome. Okay. I think I just had to press harder. Okay. Ionization energy. Come on. Alright. So, ionization energy is kind of what it sounds like, but you have to be a little bit more clear because when you say ionization, it's like, well, okay, but which one? Are you making a positively charged ion or negatively charged? cation or anion? Well, ionization energy is specifically designed or defined, well, it's defined as the energy required to remove an electron. Okay? Energy to remove an electron. And specifically, it is from a gas phase atom. That's how it's been defined. So in other words, we are creating an ion that's positively charged. So for example, if we look at something like sodium, so not that we are in everyday life going to see a sodium atom in the gas phase, but we can do this in the lab, and we could cause a sodium atom, neutral, the gas phase, to lose an electron. And usually that's done by hitting it with a photon of light. So you end up with a cation +1, and the electron is ejected. Okay, so an ionization energy, that's the energy to do this, to remove that electron. Okay, so given that, what is the trend? Alright, well, let's think about this. Let's talk about going down a group first. Okay, so when we go down a group, what are we doing? Okay, we already talked about this. Each time we go down a group, like we just talked about sodium, let's look at potassium. What has happened? We have filled an entire shell, and here we are with a new shell. 8 additional electrons have been added, and it's a new shell that's further away, right? We just talked about atomic radius. Well, if that electron, that outermost electron in potassium, is further away than the outermost electron in sodium, it's going to be easier to remove it. It's further away. So, as you go down a group, very consistently, because it's easier to remove that outermost electron, that means we put in less energy, so the ionization energy decreases. Ionization energy, come on, ink. It's so funny, I just dipped it in, why isn't it? Yes, come on. Okay, ionization energy. What did we just say? Ionization energy decreases. All right. Now, what about across a period? Yes, we are doing chemistry in the middle of the night on a Saturday night. It's true. Yes. Okay, across a period. guess it depends on where you are in the world, though, right? It's not middle of the night for many people, but it is for me. Okay, across a period, what happens? Let's think about what we talked about with the atomic radius. Across a period, the atoms were getting smaller and smaller and smaller, right? So that means those electrons are closer to the nucleus. Those negatively charged electrons are held more tightly by the positively charged protons, right? So that means that those outermost electrons will be more difficult to remove. And so that means we would have to put in more energy to remove them. So, across a period, it follows that the ionization energy increases. Okay. So, down a group decreases, and this is I always like to include explanations too. This is due to the increased distance. We can think about Coulomb's law. So due to, and I'll say because, increased distance, proton electron distance, ionization energy increasing across a period. A couple things going on. We've got, so put because of, we have decreased distance, with our proton and our electron, but also increased something called effective nuclear charge. And that is essentially this idea of what is the charge that an electron feels, if we want to anthropomorphize the electrons. What is the charge that an electron feels from the nucleus? So we could imagine that, say, this electron in carbon feels a +6, and this feels a +5. Now, it's not exactly that because we have these inner electrons. This shell is shielding a little bit of that positive charge from it. But essentially, that's what we mean when we say effective nuclear charge. That it is increasing across a period. So those electrons feel the positive charge and they get pulled in. That is causing this decrease in the radius, and it's causing that closer proximity of the electrons to the protons, and it's therefore more difficult to remove the electrons. And so there we have our periodic trend for ionization energy. ionization energy. Here I wrote out this process of having a neutral atom and removing an electron. Let's talk about how that affects the radius when we have a neutral atom and then creating a cation from it. Okay, so let's think about this. How do these radii differ from each other? Here we've got a full neutral atom. And let's write out, if you remember, if you've learned this before, electron configurations. And if you have no idea what I'm talking about, then this is going to work even better to help you fall asleep. Okay, so let's write out the electron configuration for sodium. We have 1, come on, get that ink flowing, 1 S2, 2 S2, 2 P6, and then 3 S1 is the valence electron in the outermost shell. So when we remove this electron, that electron originated from the 3s1 orbital, or from the 3s orbital. It's that one there. So that means if we were to write out the electron configuration of our ion here, it no longer has this 3s1, since that's where that came from, and now it's gone. So for this sodium ion, if we wrote out the electron configuration of it, we would get 1s2, 2s2, 2p6, and that's it. So what do you think? If we compare the sizes of these two entities, this neutral atom and the cation that formed when we removed an electron, which one's bigger? Yeah. We have removed this electron. This is going to be smaller for sure. Okay. Cation. So the cation that's formed from its original neutral atom, it's always going to be smaller. So if we compare the radii, this is larger. So what if we created an anion? What if we did the opposite? So if we took something like what creates an anion? What's an example? What do you think? If we look at a periodic table, how about fluorine? That's a quintessential nonmetal that gains an electron. Yes, indeed. Okay, so let's look at fluorine. Draw my little barrier there. Oh, goodness. Okay, so if we have fluorine, once again, going to do all this in the gas phase. And we're just looking at atoms by themselves. So here's a neutral fluorine atom in the gas phase. And if it gains an electron, so now I write it that way. It becomes fluoride. Still gas phase. Okay. So let's do that same thing if we write out the electron configurations. And this is 1s2, 2s2, 2p5. It gains an electron and becomes 1s2, 2s2, 2p6. Okay. So now we've got an additional electron. It is now filling this entire shell. And by the way, this has the same electron configuration as what? As neon. So we can write this. One of the notations is putting it in brackets for the noble gas that has the same electron configuration as that. It's neon. And this has more electrons. So if we start out with a neutral atom, in the case of fluorine here, and this time we are creating an anion, adding an electron. So now this is going to be larger, right? And side note, fluoride, 1s2, 2s2, 2p6 is neon. What was our sodium cation? 1s2, 2s2, 2p6. That is also neon. Same electron configuration as neon. So no wonder sodium plus 2, I don't know why I said that, sodium plus 1 is so stable, is it has the same electron configuration as noble gas, very inert, unreactive. And same with fluoride. Very inert, very stable once it becomes fluoride. Fluorine, very reactive. Now, fluorine naturally does not exist as an atom. It's F2, it's a diatomic. But either way, very reactive. Sodium metal, very reactive. Putting sodium metal in water is so much fun. That thing explodes and there's flames, and like seeing flames come out of water, you know, who sees that? You don't get to see that very often. Super cool. Okay. So one last trend I'm gonna mention before I close down for the evening is I wanted to talk about electronegativity. And I wanted to distinguish it from Electron Affinity. So, a lot of people I hear electronegativity. A lot of people I hear say electronegativity is the ability for an atom to attract electrons. Period. And they don't say anything else. And the problem with that is that it's tempting to then assume we're talking about this process of an atom gaining an electron to become an anion. But no, that process is called electron affinity. Okay, so I didn't say that before, but I was generally just talking about creating an anion. But the electron affinity, that is talking about the energy required or released, I should just say the energy change that is associated with an atom gaining an electron. All right. Whereas electronegativity, this is always in the context of a chemical bond. I'm going to write bond in big letters. Okay. So in other words, we're always talking about an element that is in a molecule, and then we are discussing how well that element is pulling electrons away from another element that it is bonded to. So actually I could show you some examples here. I have these structures sitting around, so we could use these as examples. So here, if we have two different elements, and in fact, I should probably, I'm going to do it this way. I'll talk about a specific molecule, and this is ammonia. Okay, so I'm going to write the structure here, including a lone pair of nitrogen that's bonded to 3 hydrogens. And this takes what's called a trigonal pyramid structure. And it looks like this in 3 dimensions. So, side angle, you can see it is not perfectly flat. It's hard to see when you're looking at it bird's eye view. But from the side, I have a little camera on the side. You can kind of see that this is a little stubby thing. It's a little pyramid. Okay. Nitrogen is more electronegative than hydrogen. And so what it is doing, it is pulling electron density away from the hydrogens towards the nitrogen, because once again, nitrogen is very good at pulling electron density away from other elements that are less electronegative. And part of the reason for that is it has a pretty large effective nuclear charge. So pulling electron density away from the hydrogens means we end up with a polar molecule. Alright? So the larger electronegativity that nitrogen has compared to hydrogen results in some very powerful properties. It changes the melting point and the boiling point significantly, and it, especially when you start looking at molecules like water that are very commonplace on planet Earth, it can have huge repercussions. So understanding electronegativity and chemical structure in 3 dimensions really helps you understand a lot of chemical properties, chemical reactivities, different types of chemical reactions, a lot of organic chemistry. It's huge. But once again, it's just for a bond. It's not talking about creating a full anion. So we usually see more discussions about ionization energy and electron affinity when we are talking about ionic bonds and creating ions and then creating these ionic structures. Whereas electronegativity, this usually comes into discussions a lot more often when we're looking at covalent bonds and the molecules that result from covalent bonds. And just to wrap up, the periodic trend for electronegativity is similar to what we just saw for ionization energy. And how I always remember it is essentially that fluorine is the most electronegative. Fluorine. So I always say, alright, here's fluorine. Fluorine, number 1. Most electronegative. And then everything else is essentially increasing as you go towards fluorine, either up or over. Okay, so increases this way, increases this way. So if you just remember fluorine being this small atom with large effective nuclear charge, it is the most electronegative. Oxygen is the second most electronegative. So we're essentially just seeing all of these are going to be less, and same over here. We're going to have smaller electronegativities. So it follows that francium has the lowest electronegativity on the periodic table. All that said, these are general trends. So you can have some really strange things happen in the middle of the periodic table. For example, you can have a metal such as gold or mercury has a higher electronegativity then, say, some of these nonmetals here, selenium, for example, maybe even bromine, it's very fascinating how high of electronegativity these heavy metals have. So we do see lots of interesting anomalies here and there throughout the periodic table. And I can't even tell you how rich the whole periodic table is in just these fascinating little tidbits here and there, and how they affect things. Like, if we look at lead and how lead can interact with sulfur in our proteins have sulfur in them, and our proteins, a lot of them, they rely on having structure that has sulfur bonds, and lead can go in and disrupt those bonds and result in lead toxicity. So many things just have these subtle little ideas, or that there are certain aspects of their reactivity that might sometimes, when you're studying chemistry, feel like, who cares? Why are you even talking about this? But it affects all of us in profound ways that sometimes we can't even imagine. And while I do know a lot of chemistry, there is a lot I still do not know. And it's something you could study for an entire lifetime and still not know all of it, which is what makes it so amazing. I love it. All right, well, thank you for joining me for this lesson and chatting about chemistry and periodic trends, atomic radius, ionization energy, electron affinity, and electronegativity. This style that I am teaching right now is totally different from the live stream that I do on Mondays. So on Mondays at 8 p.m. Eastern Time, I am really high energy. And the layout is totally different. So if you want some really solid chemistry and bring in your questions and studying or preparing for an exam, or let's just say you're curious about chemistry and you like listening about it and you're not even taking a class, totally cool. I would love to see you. And I will also, every so often, I'll be doing this ASMR style as well. And the reason why I'm trying this tonight on Twitch is because I have my ASMR chemistry YouTube channel, and so many of my subscribers there have just they just give great feedback. I can't even tell you, it's just so amazing. And they find it to be really valuable and helpful, and so I thought I'd give it a whirl here on Twitch as well. So let me know if you have questions. Come back, see me again, and I will see you the next time, whether it's here doing ASMR or if it's maybe and the high energy stuff on Mondays. So I'll see you again soon, and good night.